Okay, so then let's continue. So where we are currently at is that we now can write our GLM as follows. So we have our yi given by mu I plus epsilon I. Yeah, so we have I from 1 to n. And these are our data point predictions that the GLM does, so scalar numbers. This is our deterministic component that is given by the product of the corresponding row of the design matrix with the beta parameter vector. And this is our random contribution, so it's a random variable, which we have now seen is distributed according to a univariate normal distribution with expectation 0 and variance parameter sigma square, which holds for all of the epsilon I from I 1 to whatever, how many data points you want to predict. Now, what I will now then try to do is to link this, where we now write out basically one equation for each data prediction, to link this to the multivariate Gaussian case, so that we don't have to, if we now have, for example, 100 data points to describe our model, we have to write down 100 of these equations. And we will, I think, proceed as follows. We first briefly discuss bivariate Gaussians again. So that's when actually our n equals 2. So that was what we also looked at in the previous example. And then I want to, maybe in more depth, discuss the idea, let's call it spherical covariance matrix, because this is what I will always call it. To essentially link this idea of independently and identically distributed univariate error variables to a specific form of a multivariate Gaussian over an error vector. Yeah? But maybe before we delve into that, which is, I think, the most important thing for today, let's talk about the bivariate form again. So I hope you remember that last time we discussed the probability density function for multivariate Gaussians, and that was given with, or this denoted by this abbreviation nx, and then these two parameters, and then the whole thing was just a formula. So it was this 2 pi to the power of minus n half determinant of the covariance matrix to the power of minus 1 half, then the exponential function minus 1 half x minus mu transpose inverse of the covariance function, and again the x minus mu. So this is where we spent most of the time last week discussing the ingredients of this formula. So I assume you are familiar with that. Now let's briefly look at again at the case of a bivariate case, although we did that last time already. So we have for bivariate, which means n equals 2, or here I always say n. Sometimes it's also called d, so the dimension. But the more important thing is that that there are two scalar components to the vector of interest, that x here, which means our mu also has two entries. And this is actually where I want to talk more about now. The covariance matrix has, because it's always n by n, has 4 entries, which I now call sigma square 1, 1, sigma square 1, 2, sigma square 2, 1, and sigma square 2, 2. And I briefly want to talk about this form and its visual representation. So what you have in the case of a bivariate Gaussian intuitively is the following with the covariance matrix sigma square 1, 1. That describes the variance of x1. So the higher that value, the higher the variance of x1, meaning the marginal variance. Yeah. So of course you have a joint distribution here, and that means you have also all the resulting conditional and marginal distributions, like we discussed when we looked at the table. So there, of course, our outcomes were 1, 2, 3, and 1, 2. Here, the outcomes for each of the random variables is the entire real line, and we are dealing with probability density functions instead of probability mass functions. But the intuitions are completely the same, and also the if you actually do the math, it in the end it results in the same kind of formulas. So that is the variance of x1, and so maybe let's call that of px1 to be, so that's the marginal variance. Sigma square 2, 2, so the entry in the lower right, that's the, of course, the corresponding variance for x2. And what is actually more interesting for us are these off-diagonal elements. So sigma square 1, 2, and sigma square 2, 1. So if you think in terms of variances, and in this case then of covariances. So these are the covariances of x1 with x2. These covariances, they are always the same, so you can use your for this whole thing, you can use your intuition from correlation. It's not completely the same because correlation and covariance differ by a normalization factor, but whatever you remember about correlation, you can actually apply here. And I assume that you remember from undergrad statistics that if A is correlated with B, then also B is correlated with A. I assume that you remember that. And the same holds for the covariance, which is just essentially a rescaling of correlation. And the important thing is, of course, also that the degree to which A is correlated with B is the same degree as B is correlated with A. So these values are actually the same. So this is what this says. So whenever you specify a bivariate Gaussian, or any Gaussian, but in the case of bivariate Gaussian, you only have this 1, 2, and 2, 1. They need to be the same value. Which leads to the fact that for the bivariate case, that if you now transpose the covariance matrix, because the only thing that you change when you transpose a 2 by 2 matrix is that you exchange these two values, but these two values are the same. So the transpose of the covariance matrix is the same as the covariance matrix from in the beginning. So that's a very fundamental property of the covariance matrix. So it's symmetric. As I also already told you last time, it has another even much more powerful property. It's positive definite, which however requires a little bit more math than we can offer. So it needs to fulfill certain conditions so that it's a proper covariance matrix. So look into positive definite matrices if you feel like it. what I'm now interested in is actually the thing that you can have positive covariance and negative covariance, like you can have positive and negative correlation. And we can actually also take your intuition from correlation to this. So in the case that our sigma square 1, 2 and sigma square 2, 1, in case they are 0, so that there is no covariance, that means, of course, the same thing as that these two random variables, which are here now called x1 and x2, they do not correlate, so they are independent. And if you think about that from a correlation perspective, of course, what you would assume what happens if you look at uncorrelated data, you have these cloud of dots, which is circular. If you plot the bivariate Gaussian for the case of sigma square 1, 2 and 2, 1 being 0, you get, of course, again, what we looked at previously. So you get the probability density that is circular. Although I have a hard time making nice circles. So you get circular or spherical pictures. Yeah, so that's what we call spherical. Now, if you have positive values of so sigma square 1, 2 with sigma square 2, 1 larger 0, what's your prediction how this looks? So you have a positive covariance or positive correlation between x1 and x2. So what's your intuition? Yeah, exactly. So if you would visualize data that is correlated, you would assume something, get something like that. And this is also what we looked at last time in terms of the covariation of bivariate. And then, of course, and I will not ask that now, because you know, if you have a negative covariation, you cannot have negative variance, but you can have negative covariation. Then, of course, you get the opposite. You get this kind of pattern. Now, the whole reason why I'm introducing this or why I'm discussing this is actually because I want to get to this here. So you are, in a way, completely familiar with the fact that two things, if they are uncorrelated, they lead to these kind of spherical patterns in data that you might observe, or also in terms of probability density functions that you plot, which are, of course, different things. And we also looked at in the section before this, we looked at if one plots that from probability density functions, then one actually ends up with this spherical image. And so basically what I now want to do for the rest of this section is to generalize this to the case of, well, maybe something more in the end, to generalize this to the case of n variables. So here n has always been 2. Now we want to look at cases where n is larger than 2. And the problem with that is that one cannot plot things in more than 2 dimensions that easily as we've done here. One can one can actually plot iso spheres in 3D, but then looks already quite weird. So if n equals 3, so we will now stop plotting, but look at it from a more abstract in a more abstract way. So let's say we have x1, x2, x3, x4. So can somebody open that again, please? This thing. So we are now considering a 4-dimensional random variable as an example. Then if we talk about the multivariate Gaussian of this 4-dimensional thing, of course our mu has now 4 entries, mu1, mu2, mu3, mu4, and our sigma is of course 4 by 4 dimensional, so we have to put those in. So I stop talking to be fast. Faster. Don't have time. Come on. And this is just for 4 data points. So usually you acquire like 100 data points or something. Well, it depends. Maybe 25 or so. Then it gets even bigger. So this is how the covariance matrix would look for a 4-dimensional vector. And then, of course, the same thing as we just discussed hold. So sigma square ij equals sigma square ji if j is not equal to I. So on the diagonal, well, that doesn't, oh, well, it holds for everyone. So it's because on the diagonal it doesn't mean anything. So it's symmetric. So this value is the same as this, and this is the same as this, this is the same as this is the same as this, and so on. And what we want to build into this covariance matrix is the fact that there is no covariation between the marginal variables x1 and x2, x1 and x3, and x1 and x4. And there is also none between x2 and x3, and x2 and x4, and none between x3 and x4. So what I'm saying is that all of these values here, this, and their corresponding symmetric values, they are all 0. Yeah. So we end up with something that, so this is we end up with something, so this is all, these are all zeros, so I'm writing a 0 over them now. And we only have entries on the diagonal. And what we also want to build in is actually that sigma 1 equals sigma 2 equals sigma 3 and equals sigma square 4. So we can as well call this sigma square, this sigma square, this sigma square, because they are all the same values. And then we can write this much more without writing it out in detail, much more directly by saying sigma square times I4. What is I4? That's the 4 by 4 identity matrix. So that is the matrix that looks like this. That's I4. Now if you multiply I4 with a scalar sigma square, which is larger than 0, you get, of course, let's do that. You get, instead of the ones, you get sigma square, this, you get sigma square on the diagonal. And because this is the generalization of the bivariate case where you end up with these spherical patterns, so with something like this, These kind of covariance matrices I will also call spherical covariance matrices. Yeah? It's just the extension from the two-dimensional case, in this case to the four-dimensional case, but of course we can make that more general and call it sigma squared times IN. We cannot visualize this anymore, and you shouldn't. I mean, you can, if you want, think about how to visualize something where you have x1, x2, x3, and show me how you visualize that next time. For more than 3, this is actually impossible. I mean, you can always, it's not impossible in the sense that if you split it into multiple plots, if you do it into multiple plots, then of course you can walk through in a specific dimension at a time. So you can always, of course, visualize if you have like a 10-dimensional distribution, you can always visualize for different values of the 8 remaining random variables. You can visualize the 2-dimensional PDF. But to visualize everything at the same time in one plot, that's, I don't know how this is supposed to be. For the 3D case, it's actually already fairly hard because you have these isocontours which are wrapped in themselves. And if you make things translucent, then it's hard to see. But it's at least possible. Okay. So here what I wanted to introduce is that somewhat intuitively this idea of identical and independently distributed random variables one can in principle build in by somehow using such a covariance matrix sigma square IN and if one wants them all centered at 0, of course one needs this expectation parameter 0. So where I want to, so this is kind of wishy-washy intuitive things. So the next thing that I want to do is be a little bit more formal about the whole thing. So to basically show you that if one comes up with a proper model of independent univariate entities, so epsilon i's, then this is equally well described by such a multivariate case. Yeah. So there we should spend a little bit time on it to make this link between these independent error terms and the multivariate Gaussian to make that even more clear than we have already achieved. So we made it clear in some way now because I told you that you can use your knowledge about correlation to get to that, but one can also do that more formally, and actually that then, in my opinion, demonstrates the fact that this is actually meaningful in the clearest sense. So this is actually the part that I call IID Gaussian variables. Which maybe we, does that help? Maybe it helps. So we now, so what I want to do now is that we discussed epsilon I being distributed according to a univariate Gaussian with expectation parameter sigma, with expectation parameter 0 and variance parameter sigma square. Yeah, so that is the thing that you are very familiar with. That is this assumption, which we needed to come up, or which is built into the GLM. And now I want to link that in a more formal way to the fact that we can also think about a vector epsilon which is n-dimensional and which is distributed according to a multivariate Gaussian over this n-dimensional vector. So this is now not a bivariate case necessarily, but it's an n-dimensional thing with expectation parameter 0. So 0 in this case means it's a vector of zeros and it has n entries. And covariance matrix sigma square IN. Yeah, so the spherical covariance matrix. The aim of this exercise is to basically get away from writing the GLM equation now in this case mu I plus epsilon I for all of for all of I, for all of the i's to get to something where we can go back to our matrix notation, where we say, okay, we have a vector y here, which is n-dimensional. We have mu I, which is n by 1, but is actually coming from this matrix product, so from this n times p times p-dimensional vector, plus an n-dimensional, and that's the important part here, an n-dimensional vector. Yeah. So this is why I want to get to this n-dimensional representation of the epsilon I. Yeah. So that's where I want to get to. Questions of where I want to get to. Who's lost? No one's lost. If you don't tell me that you're lost, then I don't know if you're lost. If you are lost, let me know, then we can clarify things. Nobody's lost. Good. Now, what to actually do this? You need to think back about of the and actually basically to make this link very explicit, you have to think back of the model for stochastic independence that we discussed. So what do you remember about our model for stochastic independence? So so remember we had something like this, a joint distribution of two random variables. If we now want to model that, if you now want to model the case that x and y are independent, because that's what we want to do with our epsilon I, and they supposed to be all independent, how do we have to write the joint distribution?
The joint distribution is the product of the marginal distribution.
Yeah, the marginal distributions. So that's something that we discussed in the context of a probability theory, and we gave some intuition to that why this product or this factorization, I always call this also factorization to the marginals, builds in the idea of stochastic independence. Now, one can of course extend this to more than 3 random variables. So for example, let's do the case of 3. Then of course it extends as predicted. So if we want to have a 3-dimensional distribution, which a joint distribution which models the case that x, y, and z are independent random variables and mutually independent. So x is independent of y and x is also independent of z, and importantly z is also independent of y. Then this full factorization into the 3 marginal probability distributions is the model for that. And of course this can be then extended to the n-dimensional case. So what I'm saying is that if we want to model n independent Gaussian random variables, univariate Gaussian random variables, we can write that in this way. So this is the product. So this is just the product sign, like the sum sign. I don't know, I think we talked about the product sign briefly. It's just the same, completely the same connotations and meaning as the sum sign, just for product. And this is a univariate Gaussian. So what's behind this is of course just the 1, 2 sigma square x minus 1/2 sigma square epsilon I minus the expectation parameter, which is 0 square. Yeah, and what is written here is just the product over all of those where the epsilon I changes and goes from 1 to n. Now, what I've been claiming all the time is that this is our model for the case of n independent and identically distributed Gaussian random variables, that this is the same functional form as writing a vector epsilon, the entries of which we call, of course, epsilon 1 to n, with n-dimensional expectation parameter 0 and spherical covariance matrix. Yeah, so this is what I'm claiming, and this is not necessarily that easy to see. I mean, that this is what I'm saying all the time, that you can use, you have independent univariate random variables, and you can represent them by a multivariate Gaussian with this spherical covariance matrix. And this actually I want to show you in a little bit more detail so that you believe me. Yeah? So what we're trying to do here is have our independent epsilon I, like I showed you in this, just to make that clear again, like I showed you in this picture, where this one doesn't affect what the outcome of this one is, and this one doesn't affect what the outcome of this one is, and all of them, they don't affect each other. And this is our model for this using univariate Gaussians, and this would be the model using multivariate Gaussians. And to show that these two probability density functions that I wrote up here, so on the left hand I wrote up univariate, the product of n univariate Gaussians, and on the right hand I wrote up one probability density function which is n-variate. One has to look a little bit into the details, but that doesn't hurt that much. So let's maybe first write out what we here have on the left hand side actually. So we have this, and then this is, like I said, just an abbreviation for this. Oops. Zero minus, no, let's do it the other way around. Epsilon I minus 0 squared. So for 0 you can also, of course, think mu, if you like that more. Now what we have here is n times this factor here. So we have n times, so you could, of course, write that now out multiple times, but I mean, you see it in the script as well in 621. There are n times these, this factor, so we have this to the power of n. And yeah, well, I mean, one could, if you looked into exponentiation a little bit over the weekend, which you spent in Jana's class, I assume, then you actually here have 2 pi sigma square to the power of minus 1/2. Remember, square root and dividing by it to the power of n. So you have here 2 pi sigma square to the power of minus n/2, which you might now already recall. Do we actually write that up here somewhere? No, we didn't write it up. Which you, oh, there we go. Where you already see parts of the thing that we are wanting to get at. We also have here this we can then, of course, also take apart into 2 pi minus n half sigma square to the power of minus n half. So what I'm trying to now, I'm trying to link these two representations, and we got a little bit now already from the univariate case to the multivariate case, just by showing that this constant factor at least looks a little bit similar to what we will expect, what we expect. So the next thing that we can look at is actually this product of all these exponential terms, and all these exponential terms. Of course, they correspond to something xa, xb that you are also familiar with from last time, so that you can write these products of many exponential terms as the exponential of the sum of all these terms. So you can essentially represent this. So minus 2 sigma square and epsilon I minus 0 square. You can either multiply all these exponentials, or you sum or you take the exponential, mistake you always make, or you take the exponential of the sum of these terms. Go away. So you can do exponential minus 1, 2 sigma square sum over I from 1 to I minus 0 squared. This is now not a minus. Why doesn't it want to go away? That's an equal sign now. So this is also a part of what we will need. So basically you can transfer these product exponentials into the exponential of the sum. So here we have something, there we have something. Maybe then it's also time to look at the other side. So if we think again about our n epsilon 0 sigma square in, that was defined as let me guess 2 pi minus to the power of minus n half. We've seen this for the left hand side already. Then the determinant of the inverse, sorry, no, not the determinant of the inverse, but the determinant of the covariance matrix to the power of minus 1/2. Maybe I write it out first. Minus 1/2 epsilon minus 0 inverse of our covariance matrix and epsilon minus 0 t. Any mistakes here on what I'm doing so far? No? Good. The question is, what is the determinant of sigma square in? Does anyone know the determinant of a diagonal matrix by any chance? So this is of course the matrix that we discussed earlier, so it just has sigma square all over it. No, it's actually not 0. That would be also bad because we have to divide by its square root. No, the determinant of a diagonal matrix is just the trace of that no, not the trace. Well, is it a trace? No, I think it's a trace. It's the product of the diagonal entries. Yeah. So it's, I mean, you can see that if you think about a 2D determinant, then of course you have a times b minus 0. Then you can generalize this intuitively. So here you get actually sigma square to the power of n to the power of minus 1/2. So this means sigma square to the power of minus n half. And I think that was what we also got here. So remember, this was coming from the left-hand side. Now we recovered it from on the right-hand side for the multivariate case. This we already had. So this we have, this we have. And now let's look at what we actually have here. So here we have the inverse of sigma square times in. We have this matrix to the power of minus 1. I mean, if you learned how to do inversion of small matrices by hand, you can maybe try it for 3 or 2 by 2 matrix, and then you might see that quite easily. However, I can also tell you what that is. That's also for diagonal matrices. It's always the same. So if you have a diagonal matrix, so for example, a matrix A 0, 0, 0, A, 0, 0, 0, A. If you multiply that by the multiplicative inverse on the diagonal of this, then you have found the inverse. So if you do the matrix product here, you get A times this, and then everything else is 0. So you get to 1, 0, 0, 0, 1, 0, 0, 0, 1. So the inversion of a diagonal matrix is really, really simple. You just need to invert the entries on the diagonal and write them again on the diagonal. So here you get then sigma square minus 1 to the power of minus, well, let's do it differently. Do it 1 over sigma square on the diagonal. So, and zeros everywhere else, which you, of course, you can also write as 1 over sigma square times in. Yeah, so this is now this thing. Then you know that the in doesn't do anything, so we might as well get rid of it. And then here you have a this 1 over sigma square still in there. So you have a scalar which is multiplied with some vectors here. So you can also based on what you know about scalar multiplication of matrices, you can take this out, so you can write it in front of the whole thing, and you are left with this epsilon minus 0 transpose epsilon minus 0. And then, so we now transformed everything by basically looking at this. And then we have to transform a little bit more by thinking about what this thing actually means. If you write that out, so this is epsilon is an n-dimensional vector, this is an n-dimensional vector, so you get epsilon 1 minus 0, epsilon 2 minus 0, going on to epsilon n minus 0, after the transposition, of course, times epsilon 1 minus 0, epsilon 2 minus 0, epsilon n minus 0. And we looked at something similar last time when I told you that transpose is essentially squaring. So it's still squaring and a summation. Now if you do the matrix product again, then you of course end up with sigma square sum over I from 1 to n epsilon I minus 0 square. And this is exactly the same thing as we had here. So I reformulated. This was maybe not the most elegant way to do that. I mean, one could also write this as a long sequence of equalities, but I reformulated the left-hand side first. So I first reformulated this bit here, and then I reformulated this bit here, and if you believe my scrolling and showing you there and there and there, I showed you that they are the same. I mean, you can again look at that, of course, in the script. But what this means for us is fairly important, namely that we can write the assumption of these independent random error contribution epsilon i's independent and identically distributed. So they are identically distributed because they all have this n, this normal distribution with expectation 0 and variance parameter sigma square. They are independently distributed because we put up the product. We can write this using a multivariate Gaussian where we, as components for the n-dimensional vector, take the epsilon I, we take a long vector of zeros, of n zeros, and importantly, we take this spherical covariance matrix. Yeah? So this saves us a lot of writing, and I've shown you also that this holds, that these two probability density functions are exactly the same thing. So if you give me a value that specifies the n values that these epsilon I can take on, if I compute the probability density for this vector using this or using this, it's the same thing. Yeah. Good. And I think I have to stop here. But maybe before I completely stop is that we actually, just to summarize what we've achieved. So we've seen now for the case of simple linear regression that we can formulate that GLM in this case as follows. So we have y, which is n-dimensional. We have x, which is n times p. Beta, which is p times 1. And our epsilon, we can now write as epsilon being distributed according to a multivariate Gaussian with over this epsilon, which is also an n-dimensional entity, with expectation parameter zeros, and 0 is also an n-dimensional vector, and covariance matrix sigma square in, where this is of course the n-dimensional identity matrix, and sigma square is a value larger than 0. Yeah, so this is where we are at now, and I have to, I want to add one or two more things about this next time, so that we can actually talk about y as the random variable, but then we're actually done with model formulation. Good. Any questions? No, the clock says 47, so no? Good. Then see you this afternoon, on Thursday, or next week. Goodbye.